So we're going to move into 3.5 transformations. Now transformations is very graph heavy. It's all about moving graphs, stretching graphs, flipping graphs, stuff like that. So we're going to start with, we called these the parent functions or toolkit functions. I believe we've seen them before. I call them parent functions. That's just kind of how I learned them. But they're the basis for a lot of graphs. Like they're kind of the simplest form of square graphs or cube graphs or absolute value graphs, and then from there we say, okay, if that's the simplest form, what happens if we move it? Or what happens if we have this graph? Can we look at it and try and relate it back to one of these forms? And what's new about this slide, even if we have seen it before, is now I'm putting points on the slides. So I didn't put it for the first graph, the f of x is equal to c. All of the points on that graph, since it's a constant, are just have c in the y value. So 0c is a point, 3c is a point, 20c is a point. So we don't do a whole lot of transformations with it, but if you want to know key points, you can, as long as you have a c as the second value of your point, it is a point on that graph. But moving on from that, the f of x is equal to x graph. This is kind of the classic line. It has an intercept of 0, 0, slope of 1, up 1, over 1. And so 3 key points on every basic graph, every f of x is equal to x graph, is -1, -1, 0, 0, 1, 1. And those are going to become very important when we get into transforming, because we're going to start with those key points and then start maybe moving them or flipping them or stretching them. So the same idea for the absolute value graph of x, similar points, except for the first key point is -1 to 1, 0, 0, 1, 1. Squared graph actually has the exact same points as the absolute value graph, which makes sense because they kind of have to stay positive, but the shape's a little bit different. So when you're sketching it, you should take account the fact that the x squared is a parabola where absolute value of x is just a straight graph. X cubed has the same key points as f of x is equal to x, -1, -1, 0, 0, 1, 1. The f of x is equal to 1 over x graph is a parent function, but we don't really see that often with transformation, so I didn't write the key points with that. They're kind of gross fractions. We do see it a bit, and we will see it a little bit later, but for this section, it's not really helpful to know those key points. Square root of x, key points are 0, 0, 1, 1, 4, 2, and cube root of x is -1, -1, 0, 0, 1, 1. I mentioned shape is very important. What's kind of nice about the display that we have right here is that we have the domain and range as well. Now, if this shows up on the test and it's not a take-home exam, or even if it is a take-home exam, I'll probably tell you, yeah, there's a lot of points to be concerned about. There's a lot of these parent functions, but really only worry yourself about the x squared graph or the x cubed graph or something, because that's what you'll have to transform from. Now, the first transformation is translations, which is a fancy word to say we move it around. We move it up, we move it down, we move it left, and we move it right. So if we're going to move a graph up, we're going to add b outside of the function. And if we're going to move it down, we would subtract b outside of the function. If we're going to move something to the left, now this is kind of opposite of what might make sense to you. If we're moving something to the left, we actually add. So if we add 3 to my graph, that's going to shift it to the left. Going to go -3. And opposite, if I subtract from the inside of my graph, I'm going to move right that amount. It's not b units, it's d units, it should be d. Now, something that's worth mentioning, this is kind of a thing with transformations, is that if you're talking about vertical things, y values, moving up, down, flipping it vertically, stretching it vertically, you're tending to do that to the outside of your function. So you have your function, your parent function, let's say x squared, then x squared plus something will move up or down. While if you want to move or do something horizontally, flip a graph horizontally, stretch it horizontally, translate it horizontally, you do it inside the function. So that would look like, again, if we have the parent function of x squared, I would have x plus 2 squared, so inside my parentheses. We'll see that in a couple of examples, but that's just something to keep in mind. Okay, so let's see our first example. We are going to want to graph the absolute value of x plus 3. Now, as kind of a reference point, we have in the bottom left the graph of what f of x is equal to the absolute value of x looks like. It's just the absolute value graph. And we're going to translate that. We're going to do some sort of transformation to it. So it's important to write down the key points of the absolute value of x. So the absolute value of x are -1, 1, 0, 0, and 1, 1. We saw that kind of from the first slide. And now we want to find what the key points are going to be on our new graph after we do some sort of transformation. And what we're doing is we're moving up 3. It's outside of the absolute value, so we're moving up 3. That means I'm going to apply my translation to my y value. So I'm going to do +3 to each of the y values. So my first point will become -1, 4. My second point, if I add 3 to the y value, becomes 0, 3. And my last point will become 1, 4. Now, in order to graph this, what we're going to have to do is we're going to have to plot our 3 points. So we would plot our 3 points in this graph 0, 3. We would plot 1, 4 and -1, 4. And then what we would do is we would just sketch a graph through those 3 points and make sure that it maintains the same shape. So I kind of did all of those steps in one. I'll kind of break it down a little bit more in a later example. But the idea here is I plot those 3 points. If you're showing your work for an exam or a quiz or something like that, you should probably indicate those points, make sure that you've shown me the work, and then just make sure I have the general shape correct. I would draw an absolute value graph through those 3 points, and that's what my result would look like on the bottom right. Now, some other transformations we can talk about are reflections and stretches and shrinks. So as far as reflections go, it's always going to be we're multiplying by a negative. And again, it's kind of this inside-outside type of thing. If I'm multiplying it by the outside of my entire function, that means I'm flipping it over the x-axis, which means I am flipping it vertically. It's kind of almost backwards to think about it. But the x-axis is a horizontal line, so if you're flipping over that, you're doing a vertical flip. And then if it's a negative x on the inside of my function, I am flipping it horizontally over the y-axis. Now, stretches and shrinks are kind of a weird beast to think about them. In all honesty, personally for me, they seem kind of arbitrary why we're calling something a stretch or why we're calling something a shrink. I feel like you could argue either. So these are the formal definitions. I'm going to write up the formal definitions, and then I'm going to talk about kind of what I expect for the course. So the formal definition. If the absolute value of a is greater than 1, which means if I have a 2 or a 3, some sort of whole number, or I guess I could have a big fraction, something bigger than 1, I'm going to stretch my graph vertically that direction. So I'm going to be moving my points up relatively. Now, if its absolute value is less than 1, and this is kind of weird notation, absolute value being less than 1 just means it's a value between 0 and 1, so 1/2, 1/4, then my graph will look like it shrinks vertically. So it's almost like it's being pulled apart a little bit. And the same kind of logic applies. If I'm dealing with shrinks, I guess that should be stretches and shrinks. Anyways, even more evidence that this is kind of arbitrary. But same concept kind of applies to inside my function. If I have an absolute value of a is less than 1 in this case, I say I stretch my graph horizontally a units. And if I have absolute value of a is greater than 1, I'm going to stretch it horizontally. Now, first part, you have to make sure that makes sense. Reflections is a very important part of this slide. These last 2 parts, kind of, I guess, interesting concept, but if you got a little bit lost in that explanation, that makes sense. Because really what we're going to do for every transformation in this section is we're going to apply that strategy of taking 3 key points, moving them or multiplying them by something, and then finding new key points and going from there. So I'm concerned less about whether or not you can identify with something as a stretch or a shrink, and instead, if that a is outside of your function, just multiply the y values by that. If the a is inside your function, just multiply the x values by that. So really the process is much more important as opposed to kind of the arbitrary language. But if you're curious, those are the definitions. So this is what a reflection looks like. As I was mentioning, outside of the function, so my original function in this picture is the blue graph. The green graph is my vertical reflection, so that's outside of my function. I'm flipping over the x-axis. It's the vertical change, where if I'm looking at the orange function now, that is my inside my function, so I'm flipping it horizontally, or technically I'm flipping it over the y-axis. With stretches and shrinks, here in this case, again, my original function is, or my original graph is the blue graph. And if I multiply on the outside, notice how my graph gets stretched vertically. It's almost as though I'm pulling that top point, moving it up. I'm not shifting the whole graph up. Notice how not the whole entire graph moves up. I'm just kind of pulling it up. I'm stretching it. Or I am compressing it or shrinking it if I'm multiplying that by 0.5. I'm moving that down. To see in practice, I want to graph this transformation. Well, for starters, I got to kind of identify the parent function, which honestly in this case is a little bit easier said than done. But maybe looking at and kind of thinking about the big picture versus the small picture. Really, the parent function in this case is x squared. That's the only really like power or anything weird that is happening here. So that's my starting point. My parent function is going to be x squared. I'm going to pull that graph over here. And now I'm going to identify the points of f of x squared in order to find my final key points of my graph. So you might have to go back to the original slide or look at your notes, but the key points of x squared are -1, 1, 0, 0, and 1, 1. Those are points on that blue graph that we see above. And now we're going to carefully go through step by step each transformation to describe the transformations. And again, the describing of stretching and shrink I'm not too worried about. But I am concerned, okay, so we go order of operations. I'm shifting left 2. I'm going inside the parentheses. I'm shifting left 2. That's my first transformation. My second transformation is I'm going to reflect it over the x-axis, and I'm going to stretch my graph of a value by 2. But as far as I'm concerned, if you wrote on your test, I multiply by -2, great, because that's what you're doing in the process. And maybe I should have been a little bit more specific. I'm going to multiply the y values by -2 since it's outside. But yeah, that's the bare minimum, as you would say multiply y values by -2, as opposed to getting bogged down of what's the stretch and what's the shrink and really what's happening there, because that's the process. And then the last thing with order of operations is the subtraction. I'm going to subtract 1, which means I'm moving down 1. And if I'm keeping track of kind of that inside-outside logic, my first transformation is going to be applied to my x values because it is inside my parent function. It's in that parentheses. Where the next two are going to apply to my y values since it is outside of my squared function. So doing order of operations, my first transformation is shift left 2. So I'm going to subtract 2 from all of my x values. My first point will become -3, 1. My second point will become -2, 0, and my third point will become -1, 1. My next transformation, I'm going to multiply all of my y values by -2. My first point is going to become -3, -2. Second point is going to become -2, 0, and third point is going to be -1, -2. Now you might be thinking, that's weird, why'd the second value not change? Well, the y value is 0. You multiply anything by 0, you get 0. So that's perfectly fine. And then my last transformation is I'm moving down 1. So that means I'm going to apply my transformation to my y values. I'm going to subtract 1 from each term. So my final 3 key points are -3, 3, -2, -1, -1, -3. Now, what I'm going to do is I'm going to plot those points on my new graph. And I'm not even going to sketch anything yet. I'm just going to put the points there. So that's what this would look like. If my first key point is in red, -3, -3. My second key point is in blue, -2, -1. And my third key point is -1, -3. And honestly, this is probably how I should have approached my first example. But here we are. Now, I know, based on my parent function, what the general shape looks like. So at this point, I'm just going to draw a graph that goes through those 3 key points and has the same shape as my parent function. And it might be a little bit helpful to, I guess, think about what we described as a transformation. I know at the end of the day, I'm going to have a parabola that's moved around, and since it's reflected, it should be upside down. And in fact, that's what this is. I kind of expanded it a little bit, so it might look a little bit different. But that's what this graph is, just parabola, upside down, -2, -1 is my middle point, -3, -3 is my first key point, and my last key point is -1, -3.